Hello and welcome to this video. This is for the upper middle six and this is me doing the mocks. Alright, so this is question 1. I'm not going to do one video, I'm going to do like however many questions there are. So if there's 10 questions, I'll do 10 videos. Otherwise it gets too long. Alright, iron 2 compounds are generally only stable in neutral or non-oxidizing conditions because what happens is the Fe2 plus changes to Fe3 plus, it oxidizes. Even atmospheric oxygen will do this. This is why green solutions of iron 2 turn to brown if you leave them exposed to the air. Alright, because of this, it's hard to find iron 2 oxide experimentally, the lattice energy, and because of that we use a Born-Haber cycle, which is a we can measure many of the aspects of this, but if we put it all in a cycle, we can measure something that is not generally easy to measure. Okay, now this works because of Hess's law. Okay, now what does Hess's law state? It says from here to here must equal from the same place to the same finishing point. So there, they must equal the same. Excuse me. So if they start at the same place and finish at the same place, obviously the energy change must be the same. Okay, if they start at the same place and finish at the same place. All right, so let's figure out what these things are before we do any work. Let's get a nice black pen. Here we are. Now this is obviously the delta H of formation. Okay, from here to here, this is delta H vaporization. We're vaporizing the iron to go to here, and that value is endothermic 416 kilojoules per mole. Now, what we've done with this is the vaporization. Now, what we're doing is we're changing oxygen molecules to oxygen atoms. Now, this process I'm doing here, this is called the bond energy, all right? But the bond energy produces 2 moles of oxygen atoms. So we want to halve this process. So it's half the bond energy here. Let me put some numbers in so you know what I'm talking about. Right, this is 416. This is half the bond energy. So the bond energy for splitting up an oxygen is 496. So it's half that value. Here, what we're doing is we're doing the first ionization energy of iron, which is plus 762. And the second ionization energy is, I'm looking at the data book, like 1560. Okay, this is the first electron affinity of oxygen, and this is the second electron affinity of oxygen. Looks a bit of a mess, but let's add all these things together. So delta H lattice energy must equal the reverse. So we're going this way, so it's minus plus 798. We're going the reverse here. So, oops, let me put an arrow there. So it's minus 141. We're going down here. So down here now. So this is minus 1560. We're going down here. There's the arrow. This is minus 762. This one here is minus half of 4, what is it again? 496. Okay, this one. And this one is the vaporization. It's minus this number, minus 416 there. And now it's plus minus 272. So if we're very careful, we can add all these up. Now I'm going to pause the video. I'm going to add them up in case I get it wrong. Okay, 1 second. Okay, I've just worked it out, and believe it or not, I got it right. And I got minus 3915 kilojoules per mole. Now, what did you guys get wrong here? Well, you just messed up things like this, you know, the double minuses. Some of you forgot the half here. All right, let me show you what the marks were for, because some of you are wondering why you didn't get any marks for this. Right, they wanted this, just this, saying half of that. That gives you 1 mark. Okay, you needed that in there. You needed the 762. Where's the 762? This. That's another thing you needed. And you needed the 1560. You needed these 3 things for 1 mark. Okay. The second mark was for getting the right answer. Okay, so this is worth 2 marks, but there are the marks there. So all I can say is you just got to be careful. Okay, it's easy to mess these up, it really is. Okay, let's do the next one. Let me pause the video and get ready for the next one. Okay, this next one is part 2. Most naturally occurring samples of iron 2 oxide are found in the mineral wurtzite. All right, wurtzite has a formula Fe20OX, and it contains Fe2 and Fe3. 90% is Fe2 and 10% is Fe3. Deduce the value of X. Okay, well, this is, now we've got 20 ions. 20 ions. Okay, it says 90% is Fe2. So what is 90% of 20? Obviously, it's 18. And 10% of 20 is 2. Okay, so obviously you've got 18 Fe2s and 2 Fe3 pluses. All right, now what's the charge of 18 Fe2s? It's 2 times 18, which is 36. And what's the charge on 3 pluses? It's 6. So the overall charge is 36 plus 36 plus 6 is 42. Okay, now oxygen, all right, is 2 minus. So how many oxygens will I need for a charge of minus 42? Okay, because the plus charges, because of the ions, are plus 42. So I need how many oxygens to give me minus 42? So I could write it like that if you like. Minus 2, that's the charge. X is equal to minus 42, and from which we get X is 21. So the formula for this guy is Fe20O21. All right, that's how I did it. State and explain how the lattice energy of FeO compares to the lattice energy of CaO. Lots of you got this wrong. I'll tell you why you got it wrong. Because you didn't give it clear enough. Let me get a nice pen color. Let's use black, shall we? All right, now the lattice energy, okay, this is how we should do it, of the FeO is more negative. Now, lots of you said it's smaller, lots of you said it's bigger, but I want you in future to say this term, more negative. Okay? First of all, we've got that. Compare it to the lattice energy of CaO. It is more negative. That's the first thing you want to say. Why is it more negative? Well, the oxide bit is the same, so it's nothing to do with the oxide bit. It must be to do with the cationic radius. So you can say it like that. The radius of the Fe2 plus is smaller than the radius of the Ca2 plus. That's how I would say it. You can write it in words if you want. All right, radius of Fe2 plus is smaller than what is it? Ca2 plus. Okay, because of that, what does that mean? Well, because of that, Fe2 plus has a higher charge density because it's smaller. Okay, and because it has a higher charge density, there will be a greater attraction between the Fe2 plus ions and the O2 minus ions than for, or I should say than between, whoops, the Ca2 plus and O2 minus. Okay, that's how you need to answer this. Okay, so let's go through this again. First of all, please don't say bigger or smaller, say it is more negative. You could have also said more exothermic there if you wanted to. Okay, why is it? Because the radius of the Ca is smaller than the radius of the, the radius of the Fe is smaller than the radius of the Ca. You've got to mention that. This would be worth 1 mark. This would be worth 1 mark. Because of that, the attraction between the Fe2 plus and the O2 minus is greater than the Ca2 plus and O2 minus, and that's the 3rd mark. Okay. Oh, it's not worth 3, is it? But you need all 3 points, all 3, to get 2 marks. Okay, so that's not right, is it? But you need all of those 3 to get 2. Hope that makes sense. Please just tighten up your answers. That's all you've got to do. Let me stop the video. This is the next one on the mock. Heating FeO results in the formation of Fe3O4, as shown. There it is. Each formula unit contains one of those and 2 of those. Show how reaction 1 can be described as a disproportionation. Now you need both answers here. A lot of you only answered one, but you need both. So you should say, well, here we start off with 2 plus. So Fe2 has been reduced to Fe. So the oxidation number decreases from +2 to 0, and that is a reduction. Okay, and the other one, let's have a look at this. Well, again, whoopsie daisy, that's not what I wanted to say at all. This is still 2 plus, and now this goes to 3 plus. So Fe2 plus goes to Fe3 plus. So now the oxidation number increases from +2 to +3. You need both of these things to get the mark. Okay, you can't be vague. Oops, my pen's gone a bit weird. Vague, no, you've got to give specifics. Okay, and lots of you missed out there because I think you knew the answer, but you just weren't specific. Okay, let me find the next bit. Okay, so this is the next one. Fe3O4 can be electrolyzed using inert electrodes to form Fe. Write the half equation for the reaction that occurs at the anode. Now, a lot of you misinterpreted this as well. The anode is the positive terminal. Okay, so that means negative things go there, negative ions. Okay, so it's nothing to do with Fe, it's the oxide ion. So oxide turns to oxygen. All right, now obviously we have to balance that, so we need 2 of these. That's balanced in species, but it's not balanced in charge, is it? So we also have to take cognizance of the electrons. So 4 electrons are going to fall off. All right, so that will give you 1 mark. Calculate the maximum mass of iron formed when Fe3O4 is electrolyzed for 6 hours using a current of 50 amps. Assume 1 Fe2 plus and 2 Fe3 plus ions are discharged at the same rate. Okay, so let's have a look at this. Let's do this bit by bit. Let's discharge one of these, Fe2 plus. That's going to require 2 moles of electrons, and that's going to give us an Fe. All right, now apparently there's 2 of these. So let's first of all Fe3 plus 3 electrons is going to give Fe, but there's 2, so we have to times everything by 2. 2 of those is going to need 6 moles of electrons to give me 2 Fe. Okay, so here we are. Okay, let's see. And now we're going to use for 3 Fe's, we're going to need 8 moles of electrons, and it's going to give us 3 Fe iron atoms, sorry. All right, so let's see how much charge we've got. Well, Q is equal to IT. I is 50. Time is, where are we, 6 hours. So it's 6 hours times 60 minutes times 60 seconds. And if we work through this, we get 1,080,080,000 coulombs. Okay, how many Faradays is that? Well, a Faraday is a mole of electrons, and 1 Faraday is equal to 96,500 coulombs. So the number Faradays is equal to this. Number of coulombs divided by 96,500 is equal to, now I'm going to get the calculator out now. Let's go for this. All right, so we've got 1080,000 divided by 96,500, and we get 11.19. All right, Faradays. Okay, now 8 moles of electrons give me 3 moles of ions. Okay, so how much is 11.19 moles of electrons going to give me? Okay, this is the first relationship, but we found that we've got 11.19 moles of electrons, or 11.19 Faradays. So that's obviously X. Let's do X over here. X is equal to 3 times 11.19 divided by 8. Whoops, let me change that. Divided by 8. That's the number of moles of iron. This is moles, Fe. And now, but they don't want the moles, they want the mass. So I'm going to try and use the calculator once. 3 times 3 times 11.19 divided by 8, that's the number of moles, times 56. And this is going to give me grams of iron, isn't it? All right, let me turn this off and find the calculator. Here we go. Okay, just use the calculator and I get 235 grams. Okay, so that's the mass of iron. I'm checking the answer scheme as I'm going, and that's the right answer. Okay, all right, let me stop the video again and get the next bit. Okay, this next one is about batteries. LiFePO4 can be used in the lithium-ion rechargeable batteries. When the cell is charging, lithium reacts with the graphite electrode to form LiC6. When the cell is discharging, the half equations are there, that and that. State one possible advantage of developing cells such as the lithium-ion rechargeable battery. Now, you just got to learn these, eh? I wouldn't have got this either, don't worry. But small size, that's one. Compact, in other words, they're small. I don't know what the difference is there. They're low mass. Okay, they have a high voltage. Any of these would have given you one. Okay, and there we go. They're the ones from the answer scheme. But if you ever have to do this, one possible advantage, always go for small, low mass, because lithium has a relatively low mass and high voltage. All right, so let me stop this and do the next bit for you. Okay, this one, the LiFePO4 can be used in, we've done that, haven't we? Use the cathode half equation to determine the charge, if any, in oxidation, sorry, the change, if any, in oxidation states of the lithium ion at the cathode during the discharging. So here we go. We're looking at this one because it wants only the cathode. Lithium obviously starts as +1. Okay, and lithium has only got one oxidation state, so it finishes at +1. All right, iron here, well, we should all know FePO4, the phosphate is 3 minus, so iron is 3 plus. So the iron starts as 3 plus. What is it here? Well, this is still 3 minus. This is +1, so the iron contribution must be +2. So there we go. All right, let me stop this and get the next question. It's quite a long question. Now they need an equation. Write the equation for the overall reaction that occurs when the cell is discharging. Now, all we have to do is add these two together. All right. Now, obviously, the electrons are going to cancel. The lithiums are going to cancel here. Anything else? I think that's it. So this is LiC6 gives 6C. We dealt with that, Oh, wrong one. Now I've got to put this in. FePO4, because it's on the left, gives me that plus LiFePO4. And there you go. Just add these two together and we get that. All right, that's question one done. Let me stop this now.